You guys are never ready for the class, right? Okay. So we are going through the topic of level of service and capacity analysis of uninterrupted flow facilities. There are of three types: freeways, multi-lane highways, and two-lane highways. Right now we are discussing the procedures for freeways and multi-lane highways because the procedures are same. Okay. Earlier we have discussed the definition of capacity, the explanation and definition of level of service. The last thing which we were doing was the adjustment factors. So capacity and free flow speed, when they are calculated for ideal conditions. So once you calculate them or you find them out, you can apply some adjustment factors if the ideal conditions are not met. And these conditions are related to weather, driver familiarity, incident, and work zone. Okay. Work zone has some calculations. We have seen it last time. And some of these are applied to only free flow speed, some of these are applied to capacity and free flow speed both. Okay, last time we were looking at the equations. If somehow you cannot calculate or you cannot find out the free flow speed of these highways, you can calculate them. Okay, so we looked at the equations for calculating free flow speed for multi-lane highways and freeways. Let us start with an example today. So in this example, you can see the data is given for both types of highways, a freeway and a multi-lane highway. This is the equation for calculating the okay. This is the equation for calculating the free flow speed of a freeway. Okay, and this is the data for the freeway. The 6 lane, 12 feet lane width, right side, letter clearance 4 feet. What else? There are 4 amps per mile. Okay, if I look at the equation, I need 3 things in the equation. FLW is what? Lane width. The factor for lane width, right? Okay, and the factor comes from the table which is on the slide here. So our lane width is 12 feet. So factor is how much? 0. Okay, FLC is for what? Lateral clearance. It is given as 4 feet. On the right hand side, we only need that. For 4 feet lateral clearance, we have the third row. And how many lanes we have? It's a 6 lane freeway. So how many lanes here? 6? 3, right? These are for one direction. 6 lane means 3 lanes in each direction. Okay. So my factor is this one. 0.8. So FLW is 0 and FLC is 0.8. What is this TRD? Total ram density, okay, which is given 4 rams per mile. Okay, so how much is the free flow speed? Yes, how much? Any problem? Clear? Okay.
What's the theory for the runway?
Total ambulance. Please give. Okay, for the freeway, for the multi-highway, this is the equation. Okay, again I need some factors here. What is the first thing here in the equation? Yes. Yeah. Very good. What does that mean? Huh? Base. You were saying what? You were saying no?
No, I don't know meaning.
Okay, base free flow speed, yes. Okay, and it's what? It's given, right? How much is it?
65.
Yeah. Okay, so base free flow speed 65. Okay. FLW is for the lane width, right? How much is the lane width? Look for multi and highway, okay? 11. So the factor is how much? For 11 feet, the factor is 1.9. Okay. So FLW 1.9. FLC, factor for lateral clearance. Okay, how much is the lateral clearance here? 2 feet. But 2 feet is where? Right side. Okay. Which lateral clearance are they asking for here? Which lateral clearance are they asking for? Total. Okay. I have what? Only right side. Okay. Is it given for the left hand side as well? No. So what should I do for the left hand side? Assume, right? Assume what? Somebody said something else. Yeah. Multiply by 2. Assume they are the same. Okay, any other idea? Yes. They have told us how much is the actual lateral clearance in the question, but not in numbers, in words. I guess in this table, because we are looking at the last column, right? We are looking at the last column. Okay. So what thing tells me about the lateral clearance on the left hand side? What do I have on the left hand side? What do I have on the left hand side? Median, right? Median. So which thing tells me about the median? Look at the data in the last column. Which thing tells me about the median?
Number of lines.
Number of lanes. What does number of lanes have to do with the median? Lane width. We are going like this. Okay. Then lateral clearance on the right hand side. Then access point. Undivided. Sure. Okay. Undivided means what? There is a median or no median? No median. So how much is the lateral clearance on the left hand side? 0. If there had been a space, it would have been a median, right? That means there is no space. On the left hand side, there is no space. Okay. So the actual is how much? 0. Okay. So the actual is 0. But I mentioned it last time as well. It is written here. If the highway is undivided, the lateral clearance on the left hand side will be taken as 6 feet. Okay. But you should know the actual is how much? 0. Okay, this is just we are assuming. Okay, we are assuming what? 6. Okay, we're not multiplying by 2, and we are assuming not because it's not given. Okay, it's because of some other reason I explained at that time. But if it is undivided, then we assume it to be 6 feet. Okay, so 6 we are assuming for the left hand side, right hand side is 2, total is 8. Okay, and how many lanes we have? We have 4 lane freeway, 4 lane highway. So in the first 2 columns, 2 plus 6, 8 feet, and the factor is 0.9. Okay, then factors for median type and access point density. Median type is undivided, factor is 1.6. Access points are given 20. Okay, so 5. Okay, the factor is 5. Yes.
65.6.
How much?
65.6.
Any problem? Any questions? Clear? Clear? Okay. Few things just to clarify the concepts. Now you see some of the values are written non-applicable. Okay. For example, you look at this value. Okay. For freeway, they wrote it non-applicable. Okay. Now this value for multi-lane highway is telling us about what? Undivided means no median. So why it is not applicable to freeways? Freeways always have a median. Okay, so it cannot be undivided divided. There's nothing such thing as undivided freeway. If it's a freeway, it has a median. That's it. No other option. You don't have to tell. If you say it's a freeway, you don't have to tell me if there's a median or not. There should be a median. Clear? Secondly, base free flow speed. We don't need it for freeway. We need it only for multi-lane highways. Ramp density. Freeways have ramps. Multi-lane highways don't have ramps. Access points. Freeways don't have them. Multi-lane highways have them. Clear? Okay, understood? Everybody, clear? So some of the things which are only applicable to freeways, some of them are only applicable to multi-lane highways. So you can see the differences between them. Okay. Using the level of service concept, we can perform 3 types of analysis. Okay, all these three analyses are related to level of service. Okay, so the first one is operational analysis. This is what you are doing for your term projects. Okay, now in your term project you have a segment, right? Everybody has chosen a segment. Okay, and what you will find out in the end for this segment? Anybody knows? Level of service. Okay, so in operational analysis, we have an existing segment and we are trying to find out what its level of service. Okay, clear? Then we have service flow rate and service volume analysis. Service flow rate, I have explained it in the video earlier as well. Service flow rate means the maximum flow rate for a level of service. Okay, this is the maximum flow rate for a level of service. And if you have a maximum service, if you have a service flow rate, then you can have service volume as well. So if service flow rate means maximum flow rate for a level of service, service volume means what? Maximum volume for a level of service. Clear? Okay. Every level of service has a maximum flow rate and we call it what? Service flow rate. And every level of service has a maximum volume. We call it what? Service volume. Okay, so we can have, what levels of service we have? Tell me. What are the levels of service? A, B, C, D, right? So A has a level, A has a service flow rate, A has a service volume. B has a service flow rate, B has a service volume, and so on and so forth. Clear? Clear? Okay. This is the second type. Third type is design analysis. In design analysis, we design something, right? Okay, we need to design something. So design, we design the number of lanes. Okay, in design analysis, we are designing or we are finding out the number of lanes. Clear? Okay. So in operational analysis, we find out what? Level of service. In service flow rate and service volume analysis, we find out these things. In design analysis, we find out
Number of lanes.
number of lanes. Okay, clear? If you want to do operational analysis, then you must find out the flow rate. Okay, demand flow rate. Small VP stands for demand flow rate. Okay, so what do we need here? We need capital V, which is the volume. Okay, the volume in vehicles per hour. The volume is in vehicles per hour. Then we have PHF, which is peak hour factor. We have talked about it. We have used it. We have used it in highway engineering as well. N means number of lanes. N is number of lanes. Number of lanes in one direction. Number of lanes in one direction. So if N is in one direction, then V is also one direction. Clear? Okay. FHV is the adjustment factor for heavy vehicles. Your flow will have some, your volume will have heavy vehicles as well. So we need to apply some adjustment factors for those heavy vehicles. Clear? Okay. So after finding out VP, we can find out level of service. We already covered the theoretical part. Later on, we will do some examples. Okay. But this is the last thing, almost the last thing you need. Okay. Then we have service volume and service flow rate analysis. So SF means service flow rate. SB means service volume. Okay, and you can see in both equations there is subscript I. I means level of service. I will be replaced by the level of service you are doing the calculations for. Okay, so I can be what? A, B, C, D. It goes up to what? F. Right? It goes up to F. But maximum service flow rate doesn't go up to F. It goes up to what? E. Okay? Because F happens when? Huh? Yes. But when? When do we fail?
No flow rate.
Huh?
No flow rate.
No flow rate. And that happens when? Okay. When do we have traffic jam? When you demand capacity what?
When the demand exceeds the capacity.
When demand exceeds capacity. Okay. So yeah, the thing is flow rate, we are not interested in the flow rate of F because that is not the maximum. Because now it's traffic jam. So the flow rate is not going up now. Okay. After capacity, the flow rate starts to drop. You have start to have traffic jam. So we are not, so these equations, yeah, I for these equations goes from A to E. Clear? Okay. Now what do we have here? We have MSF, maximum service flow rate. MSF, maximum service flow rate. Okay. So you see in the first equation, we have service flow rate and we have maximum service flow rate. Okay. What is the difference between them? Ideal conditions. Okay. Maximum is in ideal conditions. MSF is in ideal conditions. SF is in the existing conditions. They call it prevailing conditions. It is mentioned in the slide somewhere else. Okay. So SF means the normal conditions, the actual conditions, prevailing. Okay. And MSF is for the ideal conditions. Clear? Okay. And both cases I should be same, right? If MSF is for level of service B, then SF will also be calculated for B. Clear? Okay. What else do we have? N is what? Number of lanes. FHV is what? For heavy vehicles. Okay. And you see in the second equation, we are just taking the value from the first equation, multiplying by what? Peak hour. Okay. Any flow rate multiplied by peak hour factor becomes volume. Any flow rate multiplied by peak hour factor becomes volume. So service flow rate multiplied by peak hour factor becomes service volume. Clear? Okay. Okay, the last one is design analysis. We know everything here, right? What was N? Number of lanes. What is DDHV? Directional design highway. Something. Huh? This is what is important. This can come in the exam tomorrow, right? Huh? I'll not ask what is DDHV, right? Okay, very smart. But what is it? Anybody? We're doing guesswork, huh? Directional design, highway.
The volume and hourly volume.
You know, hourly volume. Okay, fine. Hourly volume in
In a lane.
a lane,
In a direction.
in a direction, in a lane or in a direction,
In one direction.
in one direction. When?
Speak out. Speak
Huh?
out.
When is peak hour? Okay. Anybody else? Any peak hour? Maximum volume in one direction in the peak hour, right? Okay. Anything missing? Anything missing? Yeah. Hmm? No, nothing missing. Okay. First of all, your eyes are missing because you do not read. Okay. And I know you don't read, and I keep on asking. Okay. So it's what? Now you read. Yes. What is it? Directional design hourly volume. Okay. So design is done for what? Now or future? Or past? Huh? Future, right? So not any peak hour in the future. Okay. What else? The other things we know. Okay. Now you can see here we are again using the subscript I, right? I refers to what? Level of service. Okay. So we are saying these number of lanes are required for level of service I. Okay. So this will be given from the client. I want to maintain what level of service? B or C or D. Okay. So the number of lanes will be for that level of service. The client tells you I want to maintain level of service C. And you tell me okay. Then in that case you need 3 lanes. And he says no, I want level of service B. Then it will change. Okay. Now what value in the equation will change? That will change N for each level of service.
But when designing the highway, shouldn't we always aim for level of service A?
No.
Why not?
I'll come to it. Okay. I asked the question first, right? Answer me first. Okay. Which value will change N for any level of service? Volume? DDHV will not change. If you tell me I want level of service A or B or C, demand volume will not change. Which value changes according to level of service in the equation? Maximum service flow rate. Okay, this value has a separate I, right? Does the FHV have an I? This one has an I? That one? No. Okay, so only thing changing for each level of service is maximum service flow rate. Okay, coming back to the question, why don't we design for level of service A? Because it will be too expensive. Okay, in level of service A, that means you are in free flow. Okay, you are in free flow, and this is what DDHV is what your design value, and as you said, design is for peak hour, right? So in peak hour, if you are in free flow conditions, okay, that means you have overestimated your design, right? Imagine you have 20,000-30,000 vehicles in the hour and you are still in free flow conditions. Okay, that means you have overestimated the design. The drivers are enjoying, yes, but they shouldn't. They are human beings, right? Human beings are here for tests and trials. Okay, they are not here to enjoy. Okay, so they must have delay. They might get stuck in traffic jam, and so on and so forth. Okay, this is part of life. Okay, clear? The point is, aiming for level of service A, even in the peak hour, even in the design future volume, it will be too expensive. It will be an impractical design. Okay, so when you design the building, anybody has taken the design courses, you guys must have taken the design courses, right? So what is the factor of safety? 1.2 and 1.6, right? Okay, so that means what? The applied load is how much less, or the capacity is how much more? 20% and 60%, right? Okay, we don't say, okay, we apply the entire load, okay, and the capacity is still 90% or 80% higher than that, because that will be too expensive. Okay, your building will be too strong, whether you don't need it then. Okay, you don't need to make it in this way. Clear? Okay. Now in all these equations we have a factor which is common, which is FHV, the factor for heavy vehicle. This factor is calculated using this equation. So in this equation we have two values. PHV means the percentage of heavy vehicles in your volume. Okay, your volume has how much percentage of heavy vehicles. And EHV, which is called as passenger car equivalent or passenger car equivalency factor. Okay, so PHV comes from traffic. You take your volume and then you find out the percentage of heavy vehicles. For EHV we have tables, we'll come to this discussion. Okay, but first of all, what do we call as a heavy vehicle? Give me example of heavy vehicles. What are heavy vehicles? Trucks and buses, vans. Okay. What is it? Horse cars. Okay. What else? So buses, trucks, horse cars, and vans, and other vehicles are what? Other vehicles are? No, these are the heavy vehicles, right? Other vehicles are light vehicles, right? We can pick them up, put them in our pocket and go with it, right? Huh? So you are saying them heavy because of what? Size. Okay. So size increases, the weight also increases. Okay, the weight of the vehicle goes to the tires. Okay. So according to the manual's definition, heavy vehicles are those vehicles which have more tires than a normal vehicle. Okay, a normal car has how many tires? Your father gave you a truck and told you that's a heavy vehicle, or it's a car. Okay. Okay. So 4. Okay. So any vehicle which has more than that is a heavy vehicle. Okay. Any vehicle which has more than 4, not for you. More than 4 for other people. Okay. Who are not deceived by their fathers. More than 4 is heavy vehicle. Clear? Now we were talking about EHV. Okay. EHV is passenger car equivalent or passenger car equivalency factor. Now having one truck and having one car in traffic, will they have equal effect? Which one has more? The truck has more effect, right? So EHV is the extra effect the truck has on traffic in terms of or in comparison to a car. Okay, EHV is the extra effect in comparison to a car which a heavy vehicle has on traffic. Okay, so if you say EHV or one truck equals to 2 cars, the effect of one truck is equal to having 2 cars in traffic. So then EHV will be 2. Clear? Okay. In comparison to a car, how much extra effect the truck has or the heavy vehicle has on traffic? That is EHV. Clear? Okay. Now, will there be an effect of terrain on this EHV? The terrain conditions, the gradients, will it affect the movement of the truck? It will, right? Okay, it will not remain the same. So for EHV, to get the value of EHV, we have tables. But to pick the value from the table, I must know the terrain conditions. Okay, so for terrain conditions, I prepared this flow diagram. It's given in the other slide in words as well, but I found this one to be easier for explanation. So you see the 2 main terrain conditions on the top. extended grade and general terrain. You can have extended grade and general terrain. For extended grade, I have two conditions. If you meet any one of them, it is extended grade. If you don't meet any one of them, then you are in this side. Clear? Okay, what are these two conditions? The gradient is equal or more than 3% and the length is more than 2.25 miles. Okay. The second condition is gradient is less than 3% and the length is more than 0.5 miles. Okay. So for example, the gradient is, let's say, 2%. Okay. So 2% means I'm not satisfying this condition, right? I'm satisfying the other condition. But in order to satisfy this condition, I must know the length as well. If the gradient is 2%, then for it to be called extended gradient, the length must be more than 0.5 miles. Okay, clear? Now, then we come to general terrain. Okay, general terrain can be rolling or level. Can be rolling or level. If you are here, then it's rolling. What is this? Gradient again more than or equal to 3%, length less than 0.25 miles. Okay, rolling. If not, then we come here, we check this one. Gradient less than 3% and length less than 0.5 miles. Okay. If this happens, then you check again. There's another check for level. For level, the gradient must be what? Less than 2%. So if it is between 2 and 3, it can still be rolling. Got it? Okay. Less than 3%, you are here. Okay. If it is between 2 and 3, rolling. If it is less than 2, level. Okay. So this condition, extended grade. This condition, extended grade. This condition, rolling. This condition, it can be level or rolling depending upon the value of the gradient. Clear? Okay. Any questions? Now, if you are on this side of the figure, right hand side, then you have only two possibilities, right? Either it is rolling or level. Okay. So we have this small table here, which gives us the value of the equivalency factor, level and rolling. Okay. So if you establish it is level or rolling, you come to this table, find out the value or take the value. Clear? Okay. If it is extended grade, then we have other tables. Okay, these tables. To use these tables, you must understand that even the heavy vehicles can be divided into two categories. The heavy vehicles can be divided into two categories, SUT and TT. SUT stands for single unit trucks. Okay, SUT stands for single unit truck. His car, 6-wheeler. Okay, those are single unit trucks. Okay, the ones which you see for deliveries, okay, and furniture or with them, those. Okay, these are single unit trucks. And then we have big trailers as well. Okay, those are called as trailer trucks. More than 6 wheels is trailer trucks. Clear? Okay. Now the normal configuration is single unit trucks are more, okay, and trailer trucks are less. Single unit trucks are more because some of the people think it's a car, so they have it. Okay, and trailer trucks are less. Okay, in that case, we use this table. Okay, the percentages are not important, but single unit trucks are more and trailer trucks are less. Then we use this table. To use this table, I must know three things: the gradient, the length of the gradient, and the percentage of heavy vehicles. Okay, the percentage of heavy vehicles. They call it percentage of trucks, but trucks means heavy vehicles. Trucks means heavy vehicles. Okay, so even if it's a bus, a big bus, small bus, whatever, it's part of this percentage. Clear? Okay. If single unit trucks and trailer trucks are equal, then we use this table. Again, we need the same thing. If single unit trucks are less, trailer trucks are more, we use this table. Okay? Clear? Okay. So I want to find out factor for heavy vehicles. I need two things: percentage of heavy vehicle, equivalency factor of heavy vehicle. Percentage will come from traffic. Equivalency factor depends upon terrain. If it is general terrain, then I can have level or rolling. Pick a value from here. If it is extended gradient, then you will use one of these tables depending upon which type of heavy vehicle is more. Clear? Okay. Let us see how we can apply it. So a freeway has rolling terrain. It has 12% trucks and 3% RVs. Okay, RVs means recreational vehicles. These are also heavy vehicles. Okay, so like I mentioned earlier, even if they say 5% buses and 2% trucks, you don't need to worry about them. All of them are heavy vehicles. Okay, so we will add their percentage. That's it. Okay, so 12 plus 3. So my PHV is 15%. Okay, whatever types of heavy vehicles are given, we'll just add their percentage. There is no problem with that. Okay, now they are saying that the volume observed is 3,200 vehicles per hour. Vehicles per hour. Okay, and these vehicles per hour include the 15% heavy vehicles as well. What is the equivalent volume in passenger cars per hour? So we need to convert this 3,200 vehicles per hour into whatever passenger cars per hour. Clear? Okay. There are two ways to do this. One is using FHV. Okay. To use FHV, I need these two things. The first one is given in the question, 15%. This one depends upon what? But depends upon what? Terrain. What terrain we have? Rolling. Okay, they didn't give us the value of the gradient, so I don't need to match the conditions. Okay, I will directly go for the rolling terrain. For rolling terrain, the value is 3. Okay, so EHV is 3. So give me the FHV value. Okay, how do we convert the volume to passenger cars per hour? Volume upon FHV. Okay, this will convert the vehicles per hour to passenger cars per hour. How much is that? Okay, so volume, which is total in vehicles per hour, divided with FHV, it will be converted to passenger cars per hour. Okay, any problem with that? Okay. Second approach is you can directly use the value of EHV to convert the volume. Now 15% is the heavy vehicles, right? So 15% means how many? Give me the number. 15% out of 3,200, remember. 480. These are the heavy vehicles we have. Okay, and each heavy vehicle in comparison to a car is equal to how many? 3. This is the equivalency factor, right? So each one of them is equal to 3 cars. Okay, so 480 equals to how many cars? Okay, clear? Now this 1,440 is what? Number of passenger cars now. Number of heavy vehicles was 480, right? Now you converted that 480 into passenger cars. Okay, what is the remaining now? How much is the remaining volume? Huh? Yes, yes. 15% was the heavy vehicle, so the remaining is already passenger car. How much is that?
4160.
Huh?
Oh, okay. Plus 144.
27? Okay, these are what?
Plus 144.
Yes, yes. We will do it. Yes. Okay. So these are what? These are already. This is what number of cars. Okay. So these are number of cars, which are actually number of cars, and these are heavy vehicles converted to cars. Okay. So now, if I want total number of cars, I will add these two together. Okay, they should be equal, right? Clear? Okay, so you can divide the entire volume in FHB, or you can take the heavy vehicles separately, multiply by the equivalency factor, and then add the cars. Okay, clear? Okay. Now it may happen that you have a segment in which there are more than one gradient. According to terrain conditions, we do change the gradient. Okay, if you have a segment of 2-3 miles, very often you will have a change in gradient in these 2-3 miles because the terrain conditions do not remain the same. Okay, so for example, you have a segment which has 2 gradients. Okay, and you have to do the analysis for this segment. Now you can do it for both of them separately. Okay, this much segment, this much part of the segment has gradient 1. I will do the entire analysis for this one, and then again repeat the whole process with the other gradient. You can do this. Okay, but that means you will do it, you do everything twice. Okay, what if I can combine these values into one? So I can do the remaining analysis only once. Okay, so to combine them, we calculate average gradient. Okay, we calculate what? Average gradient. Okay, to calculate average gradient, tell me gradient equals to what? What do we mean by gradient? It's a ratio, right? Gradient is a ratio. Ratio of what? Delta y over delta x, right? So this is how we will calculate the average gradient. I will find out total delta y and divide by total delta x. For example, take this example over here. We have a segment which has 2 gradients. Okay, you can see the value 3% and 5%. For each one of them, the part in which this gradient is, the length is given. So 3% is in the part of 3000 feet, and 5% is in the part of 5000 feet. Okay, so how much is delta x now? Okay, 3 plus 5. Okay, for delta y, I'll do what? Okay, so the gradient is given, the length is given, you can find out the height. Okay, so 0.03 multiplied by 3000. How much is that? 340. So the average gradient will be 340 divided by or 4.25. Okay, so anybody who is doing the analysis for this segment, he will not do it for 3% and 5%. He will only do what? 4.25%. Clear? Okay. Now let us see what segment we have, what type of segment, what type of terrain we have. We have conditions, right? Okay, let us apply the conditions. But before applying the conditions, tell me 8,000 feet equals to how many miles? Okay, 1.5 something, whatever, but so 4.25% gradient and 1.5 miles length. Okay, I go to the first condition. My gradient is more than this, and my length is more than 0.25 miles. So I have extended gradient. Don't need to check anything else. Okay, I have extended gradient in this case. Clear? Okay.
So if we check for each gradient, even if we have the average one.
No. Only average. Okay, the other two are gone. Now you have a segment 8,000 feet length, 4.25% gradient. Okay, clear? These are some other questions for your practice. You can do this. Okay, so there are 3 gradients. Again, you will add all 3 of them for delta y and delta x. Okay, and so on and so forth. It can be 3, 4, whatever number, but you have to calculate total delta y, total delta x. If there is a negative gradient downward, then what do we do?
Subtract.
You subtract where?
Put
That's
one
one
thing,
for
then the y.
Delta y. You subtract delta y, okay? Okay? Nothing in delta x. Delta x is distance. You cannot subtract distance. Okay? Y is up and down. X is in the same direction. Okay? So delta y for a negative gradient, then you will subtract it. Clear? Okay? So you can do these things. Yeah. From then onwards, we will be doing the examples only. Okay? Everything which we have discussed, capacity, level of service, and adjustment factors, everything will be now in the examples. There is no theory left in this course, but every example is different. Okay, so if you missed anything before, you didn't see the video or whatever, see it. Okay. Secondly, for the exam, come before time. Okay, it will be 40 minutes, 40. Okay, and so 40 minutes, considering some of you will come in and go out and disturb me and so on and so forth. Okay, so after that, I cannot extend the time. You get my point. You come 15 minutes late, there is a class after this, so I will ask you to hand in the paper. Okay, so don't be late, come on time, come in your section. Okay, and that's it.
How many questions?
Huh?
3 questions.
I don't know.
3.
So,
3,
but
4,
for
6. Huh?